let's see. Okay. Problem A, playoff. So we have a tournament where 2 to the power of n athletes are competing. The athletes are numbered from 1 to 2 to the n. And in each round, the athletes are paired up. And when athletes X and Y compete, if X plus Y is odd, then the athlete with the lower index wins. And if X plus Y is even, then the athlete with the higher index wins. Okay. And so given the integer n, we have to determine the index of the athlete who wins the tournament. So if you looked at the sample input, you might have just guessed that the answer is always going to be 2 to the power of n minus 1. And indeed, that turns out to be correct. So the idea is, let's see, how do I want to do this? Maybe I'll just use my notepad for now. Okay. So the idea is to notice that every odd-numbered athlete is going to win their first match. And the idea is that if we have like an athletes 1 and 2 or 3 and 4, 5 and 6, whatever, the sum of those two numbers is going to be odd. And so whichever athlete has the lower number is going to win, and the lower number in all of these cases is the odd number. And so all the odd-numbered athletes win their first match. Now from there, since all the athletes remaining have odd numbers, the sum of any two athletes' numbers will be even. And so in every remaining match, the athlete with the higher index wins. And so we have to find the athlete with the highest odd index, which when the athletes are numbered 1 to 2 to the n, is 2 to the n minus 1. So that's, so we can just print, let's just say, please move this away from the shared application. Let's see, maybe I'll just, make this small for now. Okay, so we can just print 2 to the n minus 1. I'll show you my code even though it's not exactly all that interesting. I just print 2 to the n minus 1, and then, Okay, good start. So now let's look at B. So we have an array, so let's say that we have an array and we have an operation where we can replace two integers with their positive difference. And we have to find an array of n integers such that there exists no pair where performing this operation will decrease the sum of the elements of the array. And so, that may or may not be possible, and in fact here we see that for n equals 512 it's not possible, but we have to find an example if one exists. So, so first of all, under what conditions will performing this operation not decrease the array? We need to have ai plus aj less than or equal to the absolute value of ai, so basically, I guess initially we have ai and aj, and then afterwards we have the difference and then the difference. So if the sum of the elements in the array is not going to decrease, we're going to need to have ai plus aj is less than or equal to 2 ai minus aj. Now the absolute value signs are kind of annoying to deal with, so we're going to get rid of them by making the assumption that ai is greater than or equal to aj. And if that's the case, then we need to have ai plus aj less than or equal to 2ai minus 2aj, which means 3aj less than or equal to ai. And so what that tells us in summary is that if aj is less than or equal to ai, then 3aj is less than or equal to ai. And so in other words, if we sort the array in increasing order, each element has to be at least 3 times the last. And so the best we can do is we can just take the sequence of powers of 3, so 1, 3, 9, 27, and so on, and then if there's a power of 3 in the sequence that's greater than 10 to the 9th, then no solution exists. And so my code just generates the powers of 3 in a pretty straightforward way. Start with 3 to the 0 equals 1, and then we do, and then for each I we go 3 to the I is equal to 3 to the I minus 1 times 3, And then just for convenience, because I already have this modulo defined in my template, I just print no if any of our powers of 3 is greater than mod minus 7, which is a billion. And then, if I'm able to construct an answer, I print yes, and I output the answer. Pretty straightforward. Cool. Problem C. So we have 2 rows of computers, and initially, all pairs of neighboring computers in the same row are connected, and we have to connect. Connect pairs of computers from different rows, so that are with this certain cost function, such that if any one connection breaks down, the network of computers is still connected. So, let's see. Maybe I'll draw. Maybe I'll do some drawing here. Okay, so let's see. We have like 5 computers up here, and then 5 computers down here. Should probably get my iPad for this. This is okay, and then we have our edges. And so then let's figure out some necessary conditions for when our network is going to be fault tolerant. So the key condition here is that the 2 endpoints of each row must be connected to the other row. And so that might look like this for example would be it, or it would satisfy like because this corner is connected to this cell on the other node or row. This corner is connected to this computer, and then these 2 corners are connected to each other, which is fine. So the reason this is necessary is if we don't have these edges, like let's say that I don't know, this top left corner it has no connection to the other row, then we can just cut this one edge, and this corner is disconnected from the rest of the graph. So we had better be able to reach the other row directly from any endpoint. It turns out that this condition is sufficient, and the proof is if we were to cut one of the vertical edges, one of the edges between different rows, like this one for example, we're still going to have at least one vertical edge left over, so we can get from this row to this row and vice versa, and it'll still be connected. And if we cut a horizontal edge, then the whole graph is still connected. There's kind of this loop structure where you can go from like the left half of this row to the other row to the right half of the row. And so the graph will still be connected in this case too. And so we need to find the minimum cost of constructing a set of edges containing the 2 endpoints of each row. Now, this involves a fair bit of casework. If you just do it, that way, you can do casework on like whether the 2 endpoints are connected to each other. And so, like, I think I didn't do it this way, but I think the cases would look like the case 1 is the 2 corners the 2 corners on the top row are connected to the 2 corners on the bottom row, and there's 2 ways that can work. And then you could have 1 corner on the top row is connected to a corner on the bottom row, and then the other 2 corners excluded from that pairing are just matched with arbitrary nodes on the other row. And then you could have none of the corners are paired up, and then each corner is just matched with some arbitrary element on the other row. And so you could work through all those cases. I was pretty lazy, and so, or not necessarily lazy, but I didn't want to actually think at all. But so I did it using bitmask DP. And so what I did was I indexed the 4 corners. I labeled the 4 corners 1, 2, 4, and 8. And so then I create a cost function for each bitmask where the cost of any individual corner is just the least cost of connecting that corner to the other row. And then I also have costs for each pair of corners that we could connect. And then I do a bitmask DP where I initialize initially the only state we can reach is state 0, where none of the corners have been connected yet. And then for each state and each set of corners that we could connect, I say, okay, if we can get to state I bar j, which is, or I or j, which is the set of corners that were connected already in state I, or that are being connected by transition j. And that's going to have cost equal to the cost of connecting state I plus the cost of transition j. And then we print out the answer, or the cost of state 15, which is the state where all of the corners have been connected. And someone notes in the chat that I should be a little bit more precise here, in that we're technically deleting vertices and not edges here. Yeah, but the idea works essentially the same way. No matter what vertex you no matter what vertex you remove, you're going to be able to you're going to have a left part and a right part, and the left part and the right part are both going to be able to reach the other cell. Yeah, so I recognize that this, by the way, I recognize that this may not be the easiest or most intuitive way to implement it, and now I'm kind of curious if I've got all the cases, so maybe I'll try implementing it in a way that might make a little bit more sense. Okay, so the first case is the two corners on the top row are connected to the two corners on the other row in some permutation. So let's deal with that case first. We could have a of 0 minus b of 0 plus a of n minus 1 minus b of n minus 1, or we could have a of 0 minus b of n minus 1 plus a of n minus 1 minus b of 0. Okay, so that's the first case. And then let's do this array, cost of 4. Actually, here, let me just borrow this code from my other solution. Yeah, so I'm just going to find the cost of making an arbitrary connection for each of these corners. And so then, let's see, so we have 4 cases. We could connect a of 0 and b of 0. We could connect a of 0 and b of n minus 1, and then we have cost of 1 and cost of 2. We could have a of n minus 1 and b of 0. We could have a of n minus 1 and b of n minus 1. And that would have cost of these costs. And then we could just not match any of the corners, and so that would be cost of 0 plus cost of 1 plus cost of 2 plus cost of 3. Yeah. So this is what you could do if you don't want to do bitmask DP, which is a reasonable decision. Let me just make sure that this gets AC. Let's see, and there's some questions in the chat, so let me scroll up a little and read through them. How many words per minute can I type? I mean, it varies. I've tested up to 150. But that requires a pretty good day. I guess on average, I type more like 120. Someone says bitmask DP wasn't the intended solution, I hope. Yeah, it probably wasn't. Oh, in this case, work does get AC. I just did the bitmask DP because I didn't want to have to worry about missing cases, and because I didn't want to type this, although the bitmask DP wasn't any faster to type. Someone asked me what the rating of this question is. I don't know. How many people solved it? Like 3,000. Okay. I don't know. Maybe well, I guess what's the rating performance of about 3300th or so? Is Carrot up? No, Carrot's not up. Yeah, I mean, I guess maybe 15, 1600, give or take. Actually, no, maybe, lower than that, I guess, maybe 1400, because it looks like the performance of around the rank solving this problem was 1400. Someone asked, how do you get the idea behind this? Part of it is just having solved a lot of problems to realize kind of from experience that looking at the at the four corners is going to be important. I think also a good strategy if you don't have any idea what to do is to draw a lot of sample cases on paper and start thinking about in what situations the graph is going to be connected and in what situations it's going to be disconnected. And and that's what Mayank says too. Just draw some cases on paper, see what you can come up with. Let's see. Other questions. Which keyboard? I use a Razer Black Widow. Can you explain bitmask DP? So the bitmask DP I use for this problem is, so basically cost of I, where I is a bitmask. So given a bitmask I, cost of I is cost of I is the cost of of creating a connection, including, or I guess a single connection, should say, including all of the corners included in the bitmask I. And so cost of 1, for example, is the cost of creating an edge including A of 0, which is the first element of the first row. Cost of 2 is the cost of creating an edge including the second corner of the first row, and then so on. And then cost of 5, for example, 5 is 4 plus 1, so that's the cost of creating an edge connecting corner 4, which is B of 0, and corner 1, which is A of 0, and so on. So that's how we get the cost array. Now, ans of I is just the cost of creating a set of edges, including all corners included in the bitmask I. And so initially, I just say, okay, ans of I is infinity for all I except ans of 0 is 0, because we can create a set of edges including no corners and no cost. And then for each I up to 16, I look at each of the possible transitions we can do. And then if we start with I, and then we include an edge, and then we add an edge, including the corners in the bitmask J, then we end up with the corners in the, so if we start with the bitmask I of corners, and add the bitmask J of corners, then I or J is the bitmask of corners contained in either I or J. And so that's the set of corners we end up with, and the cost is the cost that we paid to get to state I plus the cost of transition J. Yeah, so that's the bitmask DP. Someone asked me, what is ckmin? So ckmin, this is short for checkmin. This is something that's in my template, but basically checkmin of A comma B sets A to the minimum of A and B, and then returns true if A changed in that process. So if A was initially larger than B, then it returns true. Yeah, and Mank notes that you can read about bitmask DP in the Competitive Programmer's Handbook. Yeah, I believe that's right. Let me pull this up. Yeah, definitely recommend Competitive Programmer's Handbook as a reference on like some of the more standard algorithms. Yeah, section 10.5, bit operations and dynamic programming. This is a good reference for bitmask DP if any of you are curious. Okay. Yeah, so that's problem C. All right, let's look at problem D now. So we have n distinct points on a plane, and for each point, we have to find the nearest point based on Manhattan distance with integer coordinates that is not among the given n points. And we can choose any point if there are several of them. And so, okay. So the key observation here is that the distance from any point to the nearest excluded point is relatively small. And in fact, and the idea is, suppose that, so given a certain point, suppose that the nearest excluded, let me just move my zoom window so it stops bugging me. Okay, so suppose that the nearest excluded point is distance k away. Then, so then we can verify on paper that there must be O of k squared points, or then there's sort of a diamond shape. Let me draw this out actually. Yeah, okay. So let's say that we have a grid. This is a terrible grid, but that's fine. Going for speed rather than style here. Let's see. Yeah, I think this is good enough. Okay. Yeah. So let's say that we have this point in the center right here, and that the nearest point is 3, that the nearest excluded point is 3 away. That means all of the points I'm going to cross out right now, all of these points have to be included in our set 2. And so we essentially have like this diamond shape extending k. Oh, not sure how that happened. Okay. Okay, there's all my tabs again. Yeah, so we have this diamond shape extending k cells out, and then and all of those points have to be included in our set. And so then, yeah, and so then, in particular, what this tells us is that there are, or is if the nearest excluded point is distance k away, there must be O of k squared points in our set, which implies k is O of square root of n. Now, the way this is helpful is that it's going to bound a lot of possible solutions by n root n complexity. And in particular, I'm seeing a lot of people like asserting that there's just like a simple BFS solution, or that you don't need to make these distance observations. But you need this observation is necessary, because if the distance was not bounded by O of root n, then a straightforward BFS would TLE if there were too many points. So yeah, so this bounds a number of possible solutions with time complexity O of n root n. The way I did this was I said, okay, what this means is that the x-coordinate of our nearest excluded point is within k distance, or O of root n distance, of our given point. So what we'll do is for each point, we'll check every possible x-coordinate that's sufficiently close to our x-coordinate. Then we'll find, need to move zoom again, the nearest excluded y-coordinate on either side of our given y-coordinate. And this is a pretty standard set problem, so I'll walk you through my implementation. What I do is I include I make the set R for each possible coordinate, and R is going to store the set of ranges of points not in our set. And so for each point that is in our set, I remove its y coordinate from its corresponding R set, and then I have R as a set of ranges of points that are excluded. And the reason I need to do ranges rather than just storing the exact set of points is that there could be like 200,000 squared points to work with, and that's too many. So, okay, so we have our set of ranges. And then for each point, what I do is rather than explicitly bounding j by bounding the distance from from x to the x coordinates we're considering by O of root n, what I do is I just iterate over all like possible distances between our current x coordinate and the x coordinate we're looking at. And then as soon as the distance on the x coordinate is alone is higher than the best possible answer we found, then I break. And that can be shown that that's going to terminate, or that that's going to terminate after checking O of root n values of x. Yeah, that's going to terminate after checking O of root n values of x as well. And so then just for simplicity, I use this vector CV that stores like the current values of x that we need to check. So x minus j and then x plus j. And then for each, and then if c is equal to -1, so then I use c as like the optimal value of y corresponding to this x. And so what I do is the first thing I do is I find the next range before our value of y, and if this range in fact contains y, if its second value is greater than y and then its first value is lower than y, then I set c to then I use y as our x or as our y coordinate, because that's definitely the best we can do. And otherwise let me draw a picture of this actually. If we have like let's say we have our point down here, and then we're looking at the y coordinate up here, or we're looking at, I guess actually I'm using y's here, but let's say that our intervals look something like this and something like this. Then the 2 points I'm going to try are the left endpoint of the interval to the right and the right endpoint of the interval to the left, because these are the nearest 2 points. These are the nearest 2 points on like this layer to our x that we're looking at. And so if we look to the left, and so this is dealing with the case of the left interval, and then this is dealing with the right interval if the right interval decreases our distance to y. And so then I check min x with the distance of the x's, which is j, and then the distance of the y's, which is c minus y of I. And if it's lower, then I set our new answer. Yeah, so that is how we get, so that's how we get our solution. Someone asked if this solution is n square root n log n, and yeah, I believe that's correct. In practice, the constant factor turns out to work out a little better, and it's because rather than going through root n, rather than going through all root n possible values of x, and no matter what, I break immediately if j is greater than or equal to the answer, and that's helpful because that way, if like there's I find an excluded point right next to, like let's say. Let's say, for example, that like we have a point all out in the middle of the nowhere. There's not the middle of nowhere. There are no other points in the set nearby. If I find another point, or if I find an empty point next to this one, then I'm not going to like just consider a bunch more x values. Like I'm going to say, okay, this point right here is excluded. We already know like the answer is at most 1, so there's no need to consider any other values of x because we're never going to do any better. Yeah. Nita says grid BFS works in O of n because degrees are less than or equal to 4. Yeah, each individual BFS is going to work in O of n. But if you have, for example, let's see. If you have all of your points arranged in a diamond, for example, like let's say we just have, actually this is going to take too long to draw, but if you have something like this where all of your points are connected, then doing a BFS from each individual node would be too slow, because there could be 200,000 points, and then each point, and then if the entire graph is connected, then each BFS could if each BFS could actually like reach every single point, then you would be doing an O of n BFS for each individual point, which would be too slow. So the reason that this solution works efficiently is that we're not conducting the full BFS from every single point. We're able to like prune it somewhat, in that as soon as we find a okay, so he says you do BFS from excluded neighbors. Okay, yeah, that's a that's a little different, and that that does work efficient. Okay, yeah, if you BFS from each of the neighbors, like each of the points along here, then yeah, that will work efficiently. Okay. Yeah. And that you actually can get a slightly better complexity than this as well, and that should end up taking let's see, I think it should take O of n log n time, just because you're still going to need to do some set queries to find all the points to find like the points in the set that we're working with. And but then you'll save yourself a root n factor, which is this still works out fine, just because the time limit is pretty generous. It's 4 seconds, and how long did my solution take? Yeah, about 1200 ms. So still passes comfortably either way, but yeah, nice way to save yourself a little bit of time. Okay. Yeah. Oh yeah, he says you can use a hash map. Yeah, this is true. My experience is that hash maps, the constant factor of a hash map is generally even slower than the extra log n factor of a set. So, but yeah, at least in theory, you can definitely you can use that to get it down to O of n. All right, so let's take a look at problem E. So we have a bipartite graph where each vertex has degree 2. And for each tuple of integers little r, big R, we're going to create a graph consisting of the vertices of the given graph contained in the segment L, R on the first part of the bipartite graph, and then big L, big R from the second part of the graph. And so we need to create this, so we need to find the sum of the size of the maximum matching in this graph over all of those valid 4 tuples. And we need to do so in O of n squared. So the fact that each vertex's degree is 2 turns out to be really important here, because something to recall about graphs where the degree of each vertex is 2 is that we can just decompose them into cycles. And so maybe I'll try and draw this sample test case to illustrate. So we have 4 to 6, 4 to 9, 2 to 6, 3 to 9, 1 to 8, 5 to 10, 1 to 10, 2 to 7, 3 to 7, and 5 to 8. Yeah, and so we can decompose this into the cycle 1 to 8 to 5 to 10 to 1, and then 2 to 6 to 4 to 9 to 3 to 7 to 2. Yeah, and so we have our 2 cycle. And so what we're going to do is we're going to count the contribution of each cycle separately. And so now we need to find the answer for any individual cycle. And so first, let's suppose that the entire cycle is included in our subgraph. Then the length of the recall that in a bipartite graph, the length of any cycle is even. So say that the cycle has length 2k. And so like if let's just say for simplicity that it looks like here k is 3, and so we have like something like this. we can pretty quickly convince ourselves that there's going to exist a matching of size k using edges from this cycle. So the cycle contributes k to our answer. Now, what if the cycle is not included in our answer? If the cycle is not included, if the entire cycle isn't included, then we can decompose it into some number of chains. Like, let's say we have, like here, for example, we have 2 chains. Each chain is like vertex disjoint, and so we can, again, think about them independently. And so we need to find the contribution of each chain to our answer. And what we can do is we can see that if our cycle is not entirely included in our subgraph, the cycle can be decomposed into chains of edges. And we can see, and we can verify that a chain of length x, or let's say L, I guess, induces a matching of size L plus 1 over 2. So in other words, here we have a chain of length 2. We can see that like the best matching has size 1, or which is, I guess this should be rounded down. Or even we could say L over 2 rounded up. Because here 2 over 2 is 1, and indeed we can either match these 2 vertices, or we can match the 2 vertices. And meanwhile, if our cycle has, like, let's say, as another example, it has length 3, so it looks like this, then we can do this matching. Yeah. Okay. And so now what we'll do is we'll count the contribution of each individual chain to our answer. And so in order to have a certain chain in our answer, what we need to do, or we need to make sure that little l and big L are small enough and little r and big R are big enough to contain our entire chain. And then to prevent overcounting, we need to make sure that our subgraph doesn't contain the vertices, the vertices immediately before or after our chain in the subgraph. And so, as an example, let's say that we have, let's just do this. Actually, no, I don't like that. Let's do it like this. Okay. So now let's say that we have the chain consistent, that we want to like just get the chain including these first 3 edges. Or these, we'll say the first 3 edges. Then we need to make sure that we can't include this vertex, because if we included that vertex, then we would have this extra edge. And we can't include this vertex, because if so, then we would have this edge as part of our chain. All right. And so then that gives us bounds on L, big L, R, and big R. And from there, we can just use this to count the contribution to the answer. And I'll walk through the implementation to make this a little more clear. So the first thing I do is I build our graph, and then I generate all of the cycles of the graph. And this is relatively standard, so I'm not going to go through it in too much detail. The tricky part is computing the answer. And so what I do is I traverse through the cycle, and then I let k be the size of the cycle. And then for each I, the first thing I do is I store hx, lx, hy, and ly, which are the maximum and minimum coordinates of elements of our chain that are in the first component and the second component. So then I iterate over the starting position of the chain, and then I iterate over the length of the chain. And notice that the maximum length of a chain, if we have a chain going from let's say vertex 0 to vertex k minus 1 of the cycle, then that's just the entire cycle. And so in particular, I break if we're including every vertex, but if I is not equal to 0, so that way we don't overcount the chain that's just the entire cycle. And so then I update our minima and maxima. And then I also have these variables, these bounding variables that represent, that basically make sure that we're excluding the 2 points neighboring each chain. And so I update those just doing I do some math to update those. And in particular, if there's some point that we must include that's contained between 2 points in our cycle, then I don't count the current chain because then there are going to be no valid for tuples that include the chain we're looking at, but don't include any other elements that could be appended to the chain. And so then, assuming that there will be at least one, that all of our boundary constraints are satisfied, I update the answer. And so d plus 1 over 2 is the contribution for each 4 tuple in which this chain appears. And then this is the number of choices for little l. This is the number of choices for little r. And this is the number of choices for big L. And this is the number of choices for big R. And then I just print the answer. So that's problem E. And now we'll conclude by going over problem F, this is a bit of a big one. So the hard part of this problem is dealing with like the weird regeneration function, where we're increasing the health, or I guess I should explain the problem. So we're playing a tower defense game where the I tower has C mana capacity and R mana regeneration. And each second, the I tower regenerates mana equal to its regeneration rate, but it can't go over its capacity. Then we have a bunch of monsters. Each monster has a certain spawns at a certain time. It has a certain health, and when a monster passes the tower, the tower's mana and the monster's health both decrease by the lesser of the health of the monster and the mana of the tower. And we have to find the total amount of health among all the monsters that pass through the entire that pass through all the towers. So yeah, we have a weird regeneration function. It's kind of difficult to deal with, and so the main challenge here is figuring out a way to introduce more regularity into the structure of the problem so that we can work with it efficiently. And so the first observation is this. Let's say, so each monster will survive going past the first, let's say, K towers, and then will either escape or will be killed by the K plus first tower. And when this happens, the first K towers have their mana set to 0 because they used all of it to attack the monster. And the K plus first will have their health set to some other value, which may be non-zero. And so what this tells us is that throughout the entire process, we have only, let's say O of Q, of these irregular changes where one tower has its health set to a non-zero value. And so like this K plus first tower is weird, but with the first K tower, their mana is going to be set to 0, and then their regeneration follows a specific pattern that's like consistent throughout the process. And so other than that, we're just setting prefixes of the tower, and I guess I should say mana here, not health. Or we're just setting prefixes of the tower's manas to 0. So in my case, by the way, if there's going to be a stream tomorrow, yes, there will be. And so what we can do is we can decompose the array of towers into intervals, where each interval ends with some tower whose health is irregular in this way. So then all towers at in each interval except the last have whatever health or mana they get. I keep using the word health in my notes, which is why I'm saying it repeatedly now. Okay, so it's whatever health or whatever mana they get after K days of regeneration from 0 mana, where K is the number of days since this interval was set to 0. So that's how we're going to decompose the towers. And so I should do an example of this. With the first sample case, we have, so at our first monster has health 14. And so the first tower is going to do 5 damage, the second tower is going to do 7 damage, and the last tower is going to do 2 damage because he only has 2 health left. And so after one monster, there is only one interval. And including all 3 towers, and the third tower has health 2. And so that's an example of how this is going to look. So let's figure out how we can use this structure to efficiently process the monsters. For each monster, the overall idea is we're going to figure out the tower that'll kill them and how much health they'll take away from that tower. So we're going to iterate over the intervals, and oh, my Zoom meeting ended, that's fine. While the monster can survive all towers from the current interval, we'll just delete that interval and update the health accordingly. Within the interval that kills the monster, we need to find the monsters. We need to find the monsters. What's it called? Or we need to find, I guess, the tower that will kill the monster and the health the monster have when they reach that tower. So the way we're going to do this is we're going to use a segment tree, and we're going to use square root decomposition. Lot going on here. So first, let's say that our current interval was set to 0 less than square root n days ago, or I guess it's not called days. Let's say time units ago. So then what we can do is we can build a seg tree over the health of the towers and pre-compute the value of each node in the seg tree after k days of regeneration. I'm just going to say I days of regeneration for all I less than or equal to square root of n. And so then we can compute the total mana on an interval of towers after fewer than square root n days using a seg tree query. So, yeah, so that's all good. And so then that lets us compute the total mana available on that interval. And from there, if the monster has more health than that, then the monster will kill that interval, and otherwise that interval will kill the monster. And if the interval kills the monster, we can find the position at which the monster dies by binary searching on the seg tree. For the first position with enough, or where after an appropriate number of days, there's enough mana to kill the monster. Now, so that handles the case where I is less than or equal to square root n, and note that we need this root n bound in order to be able to build these seg trees efficiently. We can't build these seg trees for all possible numbers of days of regeneration because that could be O of n squared. So what if our interval was set to 0 more than root n time ago? In this case, we'll just brute force. So we'll iterate over the towers in the interval using brute force. Just go through them one by one. And this works because each tower will only have its health, because this can only happen for each tower O of root n times. Because if we set the interval to 0 more than root n time ago, then that means there's a root n gap between every 2 times that this can happen. And so notice, because there's a pretty tight bound on the times, this can only happen O of root n times throughout the entire process. And so doing things this way will take root n time or n root n time in total. So I'll show you my code. I have these two queries. I have I have my sum for the seg tree, and k is the number of and so k is the number of I guess k is like the approximation for root n that I'm using, and it's the number of like days on which the seg tree will be built. I set k to 100 here because it turned out that setting k to 450, which is more close to the square root of n, can get MLE, and so you have to set k a little lower. But luckily, the part where the sizes of our the part where the amount of time it's been since an interval was destroyed is greater than k is pretty efficient, and so it's fine if k is relatively small. And someone asked if binary searching on a seg tree works in log n time or log n squared. It works in log n time. It is possible to implement this inefficiently in log n squared, but you can definitely do it in O of log n time. And in fact, that's what I've done here. Okay. So I have this sum query method, and then I have this this element that gets basically the first element of this array in like the range L through R, whose prefix sum is greater than our health. All right, and so then I pre-compute the segment tree, and then I store like this set ev stores like the ranges that we're working with, where each range like again ends with a tower with irregular health. And so then I read in the health of the monsters, and notably, because like the maximum time is the same as the maximum number of queries, I just assume there's going to be a monster at every possible time, and then if there's no monster at a certain time, I just say that's a monster with health 0. And so for each time, I iterate through the intervals, and then if the current time minus the time of the current interval is greater than or equal to k, then I just iterate through the towers in the interval accordingly. And so then I find the health of each tower, and if the health of the tower is greater than, or the mana of the tower is greater than the health of the monster, then that tower is now has an irregular health, but the monster is dead, so we're done. And otherwise we just move on to the next interval. And if the but then otherwise, assuming that our range is non-empty, then I find the sum of the towers in the interval, and if our monster can survive the interval, if the sum of the mana is less than the health of the monster, then I decrease the health of the monster by the mana. Otherwise, I find the position at which the monster will die and account for it accordingly. And then this last case down here, I just used to handle the case where the monster is killed by a tower whose health is already irregular. And so then if the monster survives at the end, I add its health to the answer. So yeah, that's the contest. Have I been hacked yet? I have not. That is good. Don't like being hacked. It's not fun. I was kind of worried after I finished the contest because I was on 252 penalty, and this was about an hour 45 minutes in. And so anyone in the top 14, I think at the time, could have I guess actually no, it was like top, I guess it was like, I don't know who, it was a lot of people who could have passed me if they had solved F, but luckily F is not an easy problem, and so only 3 people solved it with enough time to get to all the remaining problems, and it looks like only 6 others solved it in general. Wonder who solved it but didn't do the rest of the contest. I'm kind of curious. Sort by submission time. Yeah, it looks like a few people have gotten it after the contest. Yeah, it looks like just a few people who... Oh wait, hold on. This is before the Oh wait, no, this isn't before the contest started. What am I thinking? Yeah, maybe some people were just doing the contest backwards. Anyway. Yeah, that's a contest. So... thank you all for watching. I will probably upload my screencast not too long afterwards. But yeah, I think so. We have a contest tomorrow. Should be fun. So I guess I will see you all then.